Hello everyone. Today our lecture is going to be about the chemical basis of life. So today we are going to be talking about living organisms and how they are composed of atoms. So we said that all living organisms are composed of cells, right? So now we're going to dive even smaller into atoms. Okay, so we're going to find out what atoms are. And atoms form bonds. So how do atoms interact with each other? And then at the end, we're going to talk about water and why water is so important for life and what those unique properties are. Okay? So matter. What is matter? Matter is made up of atoms. Okay? So matter is anything that has mass and occupies space. Okay, so it's a very broad and general term. And an atom is a very small unit of matter. Atoms are not the smallest unit of life. What did we say that was? Cells. Cells are the smallest unit of life, but atoms are small units of matter. And elements. So elements are atoms with different properties. Okay? So when we talk about atoms, we're talking about elements. So remember our periodic table of elements. And I have included in Canvas for you guys a periodic table for reference, okay? So here's your periodic table of elements. So all elements are just atoms with different properties, and we'll talk about those different properties. So we said that elements are just atoms with different properties. Now what happens if we put these elements together? We're going to get a compound. So a compound is just consisting of two or more different elements. So for example, if we take sodium, which is a metal, okay, and it's quite toxic, and we take chlorine, which is a liquid, and we combine them together, we get sodium chloride. So they're a fixed compound that creates salt, which is obviously non-toxic because we consume it every day, right? So it's just two different elements combined to create a compound, a different compound with different properties. Okay. So of all those elements on the periodic table, only 4 of them are going to make up the majority of all living matter. So we have a table here of all the elements in the human body. Okay, and we notice that these top 4 make up 96.3% of our body weight, including water. And obviously, a lot of this is making up water, right? Hydrogen and oxygen. And the other 2 are carbon and nitrogen. So these 4 elements make up the huge part of our body weight. And then there are 7 elements that make up a small amount. So probably the 3.7%, that remaining percent, okay? These are things like calcium, potassium, sodium. Remember we saw sodium chloride, sulfur, magnesium, phosphorus. So these guys make up a small percent. And then there's these ones down here in the blue. These are our trace elements. And even though they make up less than 0.01% of our body weight, they are crucial for survival. So we call them essential. And they're things you would never really think about that would be in our body, like zinc, boron, right? Iodine, copper. Some of these metals that you would never think of that would be in our body, right? So we said that atoms are very small units of matter, but atoms are even made up of even smaller subatomic particles. So there are 3 subatomic particles that make up all atoms. And these are going to be protons, which are going to have a positive charge. Okay, so P for positive, protons. Neutrons have no charge, so N for no charge. And then electrons have a negative charge. So E and negative, think electrons. So positive protons, neutral or no charge neutrons, and electrons as negative. Okay. Now, if we look at our atoms or our elements on the periodic table, we see that they look like this. Okay, so here is He for helium. Okay, so that's our actual element. And then up at the top we have a number, and that's the atomic number, which is going to be the number of protons, okay, which are those positively charged particles. And then at the bottom, we have the atomic mass. So we said all matter has mass. So it's kind of a weight, okay? And this is going to be made up of the protons and the neutrons, okay? So then another way to draw an element here shows the actual particles themselves. Okay, so in the nucleus of the atom, you're going to have your protons and your neutrons. So that's really making up that atomic mass, okay, in the nucleus. And then out in these shells or orbits, we call them, that's going to contain the electrons, okay? So we're always going to have the same number of electrons as we have protons so that we can even out our positive and negative charges. Okay, so if we have 2 protons, which is our atomic number, we're going to have 2 electrons in that outer shell. Okay. So now that we know a little bit about atoms and their subatomic particles, we can talk about isotopes, which are different forms of the same element. So let's take carbon, for example, okay? So they are going to have the same number of protons, but different numbers of neutrons, okay? So an isotope is going to have the same atomic number as the original element, but a different atomic mass, because now we've changed the neutron, and we said that atomic mass is the proton plus the neutrons, but the atomic number is just the protons, which is the same, okay? So let's take our carbon, for example. So carbon 12 is our element. Okay, so carbon 12 has 6 protons, 6 neutrons, and 6 electrons, because we always said our protons and electrons are the same. So the atomic number is 6, but the atomic mass is 12. So 6 plus 6, right, is 12. So now if we say, let's look at these other 2 isotopes of carbon. So we have carbon 13. Now we say, okay, we have the same number of protons, which is 6, but let's add a neutron. Now we have 7 neutrons. We still have our 6 electrons. And now we're going to have a mass, an atomic mass of 13, because we've added 1 neutron onto it. Okay. So now we also have carbon 14. So same thing, we have the same number of protons. We've now added 2 neutrons. So now we have 8 neutrons. So our atomic mass is going to be 14 because we've added our protons and neutrons together. Okay? So isotopes are very important in, say, carbon dating. So I have a video on Canvas for you guys about carbon dating. So they actually use the isotopes of carbon to figure out the age of certain things that we find in the earth. Okay. So besides carbon dating and how we can use carbon isotopes to carbon date, is that some of these isotopes are actually radioactive, meaning that as they age, as they decay, they're going to give off particles and energy, and we can actually measure those particles and energy. So not only can we carbon date, we can use these radioactive isotopes for different things. We can use them in medical diagnostics and treatment. So essentially we can use these tagged chemicals in the body, and they're going to show up on scans. Okay, so this is how we do PET scans. So we inject a radioactive isotope, and what they do is that they're going to find places of high metabolic turnover in the body, and we can actually pick that up on the scan. So here's a PET scan. We know that the brain is going to have a lot of uptake, but then we see these different masses in the body that have higher turnover, higher metabolic turnover, and so we're going to assume they might be tumors. And so then you can look at them more closely with other diagnostic tests. Basic research, right? So we can use radioactive tracers or labeled isotopes to just track where an atom goes through the body, through a system. So we can track such a compound as CO2 through a plant during photosynthesis. So we know exactly where it goes through the process of photosynthesis in the plant. And then, of course, we can do the carbon dating. We can date fossils using the half-life of radioactive carbon. So that's why we call it carbon dating. But we're actually using that radioactive carbon isotope and look at it over time and how much energy and particles have been given off over time. And we look at the ratios of the isotope to other isotopes and carbon in the body. So again, I have a great video on carbon dating on Canvas that you can check out. So it's kind of cool. So now let's do a little bit of review. So you can pause the video and answer these questions on your study guide or your lecture notes. And you're going to answer what are the 3 subatomic particles. And then for our element sodium, you're going to state what is the atomic number and what is the atomic mass. And then how many of each of those subatomic particles we have for sodium. So hopefully you were able to answer these questions and have them written down in your notes, but let's review the answers. So our 3 subatomic particles are protons, neutrons, and electrons. Okay. Now for sodium, the atomic number is 11. Okay. So what does that tell us? It tells us the number of protons. So we have 11 protons. Then that means this must be the atomic mass. And of course it's kind of strange because it's 22.99, so we'll just round up to 23. And what does that tell us? That tells us the protons plus the neutrons. So if we know the number of protons already, we subtract 11 from 23 if we round up. And that's going to give us 12 neutrons. Okay. Now, nowhere on here does it give us the number of electrons, but what did we say? Our electrons are always the same as the protons, so we're going to have 11 electrons as well. Okay, good job. So let's do a little bit more review, so you can pause the video again and answer these questions. So what is matter? Okay. What is the difference between atoms and elements? What are compounds? And what are isotopes? All right, so hopefully you were able to write down some answers for these questions, and let's go over them. So what is matter? Okay. So matter is anything that takes up space and has mass, right? So mass. And we talked about atomic mass, right? Or weight. So now what is the difference between atoms and elements? We said that elements are just atoms with different properties, right? So remember our periodic table of elements. And compounds are just at least two elements fixed together, brought together, right? Such as our sodium chloride is an example of a compound, okay, or what we know as a salt. Now, what are isotopes? Isotopes are just an element with a different number of neutrons. Okay, so remember back to our example of carbon. So our element carbon has an atomic mass of 12, but we have carbon 13, carbon 14. So that means we have a different number of neutrons, but we have the same number of protons. Okay, good job. All right, so now we know a little bit about elements and atoms. Elements are just atoms with different chemical properties. So what actually affects the chemical properties? What makes up the chemical property of an element? And it's the distribution of electrons. So electrons are around the outside of the atom. Remember, we had that atomic model, and we'll look at it again here in a minute, and we have the nucleus of the atom, which has our protons and neutrons, and then the electrons are kind of outside in what we call shells or orbits, okay? And the electrons are what are going to be reacting with other atoms and other elements. Okay, so the electrons are the ones that are directly involved in chemical bonds, not the protons and not the neutrons. So when we look at our atomic model, all the electrons are going to be in these shells or these orbits. And it just depends on the energy level of the electrons with what shell they're going to be in. So you're going to have to memorize this table and this level of electrons in the shells, okay? So in the first shell, there's only going to be a max number of 2 electrons, okay? So remember, all of our elements are going to have different numbers of electrons. So if it only has 1 or 2 electrons, they're going to be in that first shell or that first orbit, okay? Now, if they have more than that, they're going to start filling up their second shell, and they can have a max of 8 electrons in the second shell. Okay. Now, what if they have more than 10 electrons? Now they're going to start filling up a third shell and so on. So you only have to memorize up to 3 shells, okay? Because obviously we can have more than that, but we're not going to worry about that for this class. So the second and third shell have both a max of 8 electrons each, okay? So now why is this important, okay? So the lowest energy level always fills first. So we're always going to fill the first shell, then the second shell, and so on. Okay, so you're always going to fill it in the same order. And when atoms have their last shell, which is called the valence shell, whatever that may be, whether it's the third shell or the fifth shell, that last shell is their valence electron, and when the max number of electrons are in there, it's the most stable. So if we fill up that last shell, say it's the third shell, with all 8 electrons, it's going to be very stable. But that doesn't happen all the time, right? So we can have these valence shells that are less than full. And that's when they're going to react with one another. So when they don't have enough electrons, they're looking for electrons to fill it up, okay? So let's talk about how these electrons interact with each other to create chemical bonds, okay? So let's review that atomic model really quick. So we said we have a nucleus, which is full of protons and neutrons, which makes up that atomic mass. And now we have these shells or orbits around the nucleus full of electrons. So the first shell can only hold 2 electrons. Now our second shell holds 8, as well as our third shell also holds 8 electrons. Okay? So now let's do an example. So here's some atomic models of these different elements. Now don't look at them quite yet because we're going to do an example, and I have an empty atomic model filled out for you on the study guide. So let's try phosphorus. Okay. So phosphorus has an atomic number of 15. So that means we have 15 protons and we have 15 electrons. So start filling up your shells with electrons in the correct order and see what you come up with. Okay, so pause the video and work on that for a minute. Okay, so now let's go ahead and take a look at phosphorus here and take a look at our shells and how we did at filling them up. Okay, so here's our first shell full of 2. Okay, now we can fill up the next shell with 8. Okay, so that makes 10. So how many electrons do we have left? Right? So 15 minus 10, we have 5 electrons left. So there's only 5 electrons left in that outer valence shell. Okay, but how many can it hold? It can hold 8. So we're missing 3 electrons. Okay. So we said atoms are most stable when they have a full outer shell, full valence shell, but not all atoms have a full valence shell, right? Just depending on their atomic number. So what they're going to do is if they have an incomplete outer shell, they're going to react with another atom. So each atom is either going to share electrons, donate electrons, that means get rid of electrons, or receive or take electrons, so that both partners, both elements are going to try to complete their outer shells and fill them up. Okay, so they're going to create a chemical bond so that both outer shells are complete. And this interaction is going to form a chemical bond. And we have a couple different types of chemical bonds, just depending on how they share, donate, or receive electrons with each other. Okay? So what are our types of chemical bonds? We have a covalent bond. That means that the 2 atoms are going to share their electrons. That means the electron kind of spends some time with one atom and half its time or a little bit of time with the other atom, okay? So it's kind of like co-parenting, okay? They're going to co-parent that electron. Now, an ionic bond is going to transfer the electron, okay? So one atom is going to get rid of their electron, and the other atom is going to take that donated electron. Now that's an ionic bond, okay? So one gives it up completely and the other one adopts it, okay? Now hydrogen bonding is very specific, okay? So there's a weak interaction between hydrogen and another compound. So we'll talk about hydrogen bonding in a lot more detail when we talk about water, okay? So hydrogen is very specific because it only has one electron, okay? So it can be very reactive because it really, really wants that other electron in that first and only shell. So now let's go through some examples of those chemical bonds, and we'll talk a little bit more about each of them as well. But here we have a covalent bond, so we're going to be sharing electrons. So the 2 atoms are going to share the electrons between the 2 of them, okay? So let's look at carbon. So carbon has 6 electrons, so we've already filled the first 2, and we only have 4 in that outer shell. So it's looking for 4 other electrons. And those electrons are going to come from hydrogen, because hydrogen only has 1 electron, so it's looking for 1 electron as well to fill that first shell. So carbon can now create 4 covalent bonds with 4 hydrogens. Okay, so 1 carbon electron, 1 hydrogen electron. So they're all happy because carbon now has 8 electrons in its outer shell, and each hydrogen has 2 electrons in the outer shell. So now they're all stable and happy. Okay. Now, an ionic bond, we're going to have some transferring of electrons. So there's going to be one atom that's going to give up an electron and one atom that's going to receive an electron. Okay, so sodium has 11 electrons, so it has 1 all by itself in this outer shell, very unstable. So it wants to give it up. Okay, it's a lot easier to give up 1 electron and go back to its very stable 8 shell than it is to try to find 7 extra electrons to fill up that outer shell. Whereas chlorine, okay, has 17 electrons, so it's just missing 1 electron. So it really, really wants to steal it from someone. And since sodium is easily trying to give it away, it takes that 1 electron from sodium. So now we have an ionic bond, and each atom is going to be slightly charged. Okay, because sodium gave up the electron, it's missing that negative charge from the electron. So it's now positively charged. And we call this an ion. So sodium ion is Na plus because we have a positive charge because we're missing 1 negative electron. And conversely, chloride ion is now negatively charged because it gained 1 negatively charged electron. Okay, so this is now an ionic bond. And last but not least is the hydrogen bond. Okay, and this will become more apparent when we're going to talk a little bit more about covalent bonds. So oxygen is making a covalent bond with hydrogen in 2 bonds. So it's making 2 covalent bonds. But the thing is that the electron from the hydrogen is going to spend a little more time with the oxygen. Okay, so because oxygen is such a larger molecule, the electron is going to be a little more prone to spending more time with it. So essentially we say that the oxygen is slightly negatively charged, and that's what this little symbol means. Whereas then the hydrogen now becomes slightly positively charged because it's kind of losing the electron a little bit because it's spending more time with the oxygen. So now this negatively charged, slightly negatively charged oxygen is going to attract another slightly positively charged hydrogen. So now this creates a weak hydrogen bond. Okay, and we'll explain this a little bit more when we talk about water and how these hydrogen bonds give water its very unique properties. So now let's review our covalent bonds, right? So we have 2 or more atoms held together to form a molecule. So a molecule is just multiple atoms together, okay? And each bond is represented by 2 electrons. So 1 from one atom, 1 from the other, and we're going to share them, okay? So let's give our water example again, H2O. So here's our electron distribution diagram, or our atomic model, right? So each oxygen is making a bond with 2 hydrogens, 2 covalent bonds. But if we notice, we were talking before that oxygen is such a larger molecule than hydrogen that it's going to pull the electron toward it, and it's going to spend a little more time with that oxygen. Okay, so we call those polar covalent bonds. Okay, and we'll talk about that in a little bit as well. Creating a slight negative charge on oxygen and a slight positive charge on hydrogen, setting up for those hydrogen bonds. But that polarity is what we're talking about, where the electron wants to spend a little more time with the oxygen and not the hydrogen. So it creates a polar molecule. So all covalent bonds can be polar or non-polar, because remember we saw that carbon creating non-polar bonds with the hydrogen. Okay, it created 4 non-polar covalent bonds. Whereas oxygen is creating 2 polar bonds with hydrogen. Okay. So if both atoms kind of have an equal pull on the electron, meaning they're sharing that electron very evenly, then it's nonpolar. But if one atom, such as oxygen, has a stronger pull on that electron, and so there's going to be an uneven share of the electron, that bond will be considered polar, just like our water, okay? Which creates a slight negative and slight positive charge for the atoms, okay, in the polar covalent bonds. So now let's review our ionic bonds. So we said ionic bonds happen when atoms transfer electrons. So that creates an ion, right? So when an atom loses an electron, we create a positive ion. And then when an atom gains an electron, we create a negative ion. So now we have an ionic bond, which is the attraction between 2 ions of opposite charges. So they're going to be attracted because one is positive and one is negative, okay? So again, let's look at our example of sodium chloride. So we have our positive sodium ion because we lost an electron, and it's going to be attracted to chlorine because chlorine gained an electron and is now negative. So that attraction between those 2 charged ions becomes an ionic bond. And that is how we get this crystalline molecule of salt. Okay, so now we notice that these molecules are made up of these charged ions. So we have these positively charged sodiums with these negatively charged chlorines. Okay, and that gives us salt. But again, this is a fairly weak bond because we're able to break it down in water, okay? So let's look at our hydrogen bond again. So again, this is going to be a bond between our 2 polar molecules. Our example is water, right? So if we look, we have these compounds that are slightly charged now. Okay, so it's not as charged as an ionic bond or these positive and negative ions. We have a slight charge. So water itself, H2O, is a polar molecule, meaning it's creating these polar covalent bonds with oxygen and water. So we said that there's an uneven share of that electron. So we have this slightly negatively charged oxygen with a slightly positively charged hydrogen. So the hydrogen is kind of missing out on that electron. So it's feeling kind of left out. So it's looking for another slightly negatively charged oxygen. And then we're creating this kind of weak hydrogen bond. Okay, so we have pretty strong polar covalent bonds in the water, but then we're creating a weaker hydrogen bond between two water molecules. Okay. So let's review. So you can pause the video and answer these questions. Okay. So the first one is an atom has 6 protons, 7 neutrons, and 6 electrons. Draw an atomic model of this. What is the atomic number? What is the atomic mass? Okay. And then, in what type of bond do electrons get transferred from one atom to another? And then, in what type of bond are electrons shared but unequally? Okay, so go ahead and pause and answer those questions. Okay, so hopefully you were able to answer and draw out some of these atomic models and answer these bond questions. So if you drew it out, let's see, I can draw on here. Let's draw our 6 protons and 7 neutrons. So of course we're going to have our 6 and 7 in the nucleus. Then we're going to make our 2 electrons in the first one. Then we're going to have 4 in the outer one. Okay. So what is the atomic number? Okay. It's going to be 6 because we have 6 protons. And what is the atomic mass? It's going to be 6 plus 7. Okay. And that equals 13. Okay. Now, what type of bond do electrons get transferred from one atom to the other? That's our ionic bond. Okay. So ionic bond. And then what type of bond where the electrons are shared unequally? Okay. That's going to be our polar covalent bond, such as water is a great example. Okay. So now that we know a little bit about chemical bonds and how atoms interact, we can talk about chemical reactions. So chemical reactions happen when we make and break chemical bonds. Okay, so in a chemical reaction, there's going to be starting molecules, which are called reactants, and then they're going to form different molecules called products. Okay, now bonds break and form during chemical reactions, and the atoms get rearranged. So you have the same atoms, the same number, the same type of atoms in the reactants and in the products, but you're just rearranging the order and what they're attached to. Okay, so an example here is going to be, we have hydrogen. So hydrogen is bonded together, so H2, so 2 of those. Okay, so again, because hydrogen wants that other electron, so there's a covalent bond between 2 hydrogens. And then we have oxygen, and again, they're covalently bound to each other in 2 covalent bonds. So now these are our reactants, these are our starting molecules, and we're going to break some of these covalent bonds to create new covalent bonds, and we get 2 waters. So now instead of bound to each other, they're going to be bound to 1 oxygen to 2 hydrogens, and you get 2 waters. And these guys are our products. Okay? So reactants are the starting molecules, products are the ending molecules. And these are chemical reactions. So now let's talk a little bit about water, because water is the essence of life, really, right? So there are these life-supporting properties of water, and it's due to those hydrogen bonds. So the hydrogen bonds are what connect water molecules to each other. And this gives water a high cohesion and adhesion properties. So what is cohesion and adhesion? Let's talk about cohesion first. And this is the tendency of molecules of the same kind to stick together. So these are water molecules sticking to each other. And this is what gives water surface tension. So water has a high surface tension. And this is what allows things like water striders and these specific types of lizards to actually float and run on water. And check out this really cool video that I posted on Canvas for you guys of this Jesus Christ lizard running across the water. It's so funny to watch. Obviously, you know, organisms with a higher mass can't run on water because it's just not possible. But some of these smaller organisms are able to use that surface tension of water and float or run on them. So now we have adhesion. So cohesion is between the same type of molecule sticking together. Adhesion is the ability of substances to cling to other substances. So water can cling to something else. A great example of this is, and you guys, I swear you're going to do it now that, of course, we can't use straws in restaurants. We can't even go to restaurants. But when you stick your straw in water, notice that the water is going to kind of climb up the straw and it's going to be higher than the water level in the cup. Test it out. Give it a try. So this whole ability of water to have cohesion and adhesion allows trees to grow really, really tall and still be supplied by water because the water is obviously in the ground, right? And what happens is these trees create these straw-like structures, and it's actually a vascular system within the plants and the trees. And so that way the water can climb all the way up the tree into the leaves and supply it with water, which is just very impressive. So the hydrogen bonds in water also give it a great ability to stabilize temperature. And this is why as an organism that's built mostly of water, we are able to withstand higher temperatures and our blood doesn't boil, right? Our blood is mostly made of water, but we can withstand much higher temperatures than our body temperature and we don't boil, right? So let's look at this. So some of these definitions. So what is thermal energy? Well, it's the energy associated with random movement of molecules. So if we look at our little, pictures down here, we have a solid state. So all this molecule has very little movement, right? Very little thermal energy. And then as we add heat, because heat is the transfer of thermal energy from a warmer to cooler body of matter, we're going to increase the movement of those molecules, okay? And that's how solids transfer heat, and then they're going to become a liquid, and then they're going to become a gas because there's going to be increased movement of those molecules, okay? So that means that as we add heat to liquid, which is water per se, right, then we're going to become a gas at some point. But the thing about water is it can take a lot of heat, a lot of thermal energy before it turns into a gas, okay? So that's a huge benefit of water for life, right? So it can stabilize temperature, it can take a lot of heat without turning into another state, okay? So we said the water doesn't boil in our body, right? Our blood doesn't boil, but what do we do when we heat up? We sweat, right? So what's happening? So because we have so many hydrogen bonds in water, it takes a lot of heat to break down those hydrogen bonds, and that speeds up the molecules. But then a lot of heat is released when we form those hydrogen bonds back into water, okay? And then that slows down the molecules. So evaporative cooling allows the molecules with the greatest energy, they're really at the point of bursting, to leave at the surface of the body, okay, as sweat, right? So then we have condensation, and we even have some gas coming off of heat coming off of us, right? And this explains why we sweat. It's a process to allow us to maintain our body temperature without overheating. So another property of water is that ice is less dense than liquid water. And this has to do with the molecules in water. So when it's in ice form and the ice crystals are actually further away from each other instead of bringing them closer together. Okay, so liquid water is actually more dense because the molecules are closer together. So ice, therefore, is less dense and floats on water. So this is really important when we're talking about, the polar ice caps and life, right? So ice floats on water. So again, let's look at the benefits of ice being less dense than water. So we can have things like ice fishing. So life can live underneath the ice. So the ice actually insulates the water underneath. So you do have liquid water that's there for life and is not as cold and is not frozen because the ice insulates it over the top. So this is very important for life, right? So water is considered the solvent of life. And what does that mean? That means that because water is a polar molecule, that it dissolves things very easily, okay? So it allows any other polar or charged molecule to be dissolved really easily in it. So what might be another charged molecule? Well, salt is a great example. So if we're talking about salt in water, a solution is composed of a solvent and a solute. So our solvent is the dissolving agent. That would be our water. And then the solute is the agent being dissolved, such as the salt. So you have the two together and you have a solution of water and salt. So the salt is a charged molecule, right? So we have the positively charged sodium and the negatively charged chlorine. So when it's put into water, which is also a polar molecule, it's going to separate the sodium from the chlorine. So we have those slightly charged hydrogens, slightly positively charged, attracting that chlorine, and those slightly negatively charged oxygen attracting that positive sodium. So another thing about water is that it helps with the pH of the system. So life is really sensitive to acidic environments and basic environments. So it likes to be right in the middle. So when you think of acidity and basic, those are kind of bad environments for life. They're not conducive to life, right? So our body likes to live at pH of 7, right? Very in the middle, not acidic or basic. So how does water help keep our body at the right pH level? Well, sometimes water molecules can actually break up into ions, and those ions are reactive. So an acid is a substance that releases hydrogen into a solution, okay? And then a base is a substance that reduces hydrogen in a solution, meaning it takes up the hydrogen. So when we look at water, our H2O, right, it can actually undergo a chemical reaction and break apart into just OH. So it's now lost So it's lost its other hydrogen. So now the oxygen, instead of being slightly negatively charged, it is negatively charged. Okay, so now we get an hydroxide ion, or OH negative. And now the positive hydrogen, which has left, okay, now it's lost its electron completely. Okay, so it's lost the electron, so it becomes positive. So now what can happen is this hydroxide ion is able to take up it becomes a base. So it's able to reduce hydrogen in a solution. So it's able to receive the hydrogen. And then the oxygen is positive, so it's able to release hydrogen, because it is hydrogen, into a solution. Okay? So we talked about the pH scale a little bit. So we like to be at pH of 7. So it's a very neutral pH, we say. And so things that are acidic are going to be lower on the pH scale. So they're going to be under 7. So if you think about kind of things out there that are acidic, you kind of think lemon juice, soda, tomatoes, coffee. And of course, hydrochloric acid, which lives in our stomach, is one of the most acidic things out there, and that's how it breaks down our food. And then things that are basic are going to be more positive, or a higher pH than neutral. Okay, so we think of kind of baking soda, okay, bleach, drain cleaner, sodium hydroxide, even toothpaste, okay, is all more basic. Okay. So because life is so sensitive to either acidic or basic conditions, we have things that are called buffers. And so a buffer is a substance that minimizes changes in pH. So it likes to keep the pH neutral. Now, water is kind of a mild buffer, but there is something in our body that acts more like a buffer and is a very strong buffer. So a buffer is going to accept hydrogen when it's too acidic, okay? And then it's going to donate hydrogen when there's not enough hydrogen, so when it's more basic, okay? So our example of a great buffer is carbonic acid, which can then turn into bicarbonate. Okay, so carbonic acid can donate a hydrogen when it's needed because it has 2 hydrogens, and then it turns into bicarbonate, which is negative, and it can accept hydrogens if needed. Okay, so it can switch back and forth between carbonic acid and bicarbonate when needed, so that the environment doesn't get too acidic or too basic. And just to give you an idea of how sensitive we are, our blood has to really stay at a pH. I said 7, but 7.4 is probably more accurate. But if our pH falls below 6.9 or goes above 7.9, these are both fatal pHs. So you can become too basic or too acidic, and it can become fatal. So this is why we have these buffering systems within our body. And water can act as a buffer, like we talked about. It turns into OH negative and H positive. So now just kind of a food for thought, now that we know a little bit about buffering and pH. What happens in the water in our oceans when our atmospheric CO2 is going to rise? We know it is on the rise, right? And that is scientific fact. But what happens to things like the coral reef? So even though the algae in the water absorbs CO2, there's going to be excess CO2 in the water, which is going to increase the acidity of the ocean. So when you have CO2 combining with water, H2O, you form carbonic acid. And we just said carbonic acid and bicarbonate are the buffers in the body, but carbonic acid is the acidic form, right? So you're creating more acid in the ocean. So now the ocean is going to become acidic. So acidic environments in the ocean is going to be very detrimental to the marine life, right? So just something to think about how, the world is impacted by not only humans, but also now you can understand some of the chemistry behind what is happening and why maybe we should worry about a rising atmospheric CO2. All right, so hopefully you've had enough time to answer some of these questions. So what are our 5 properties of water that we discussed? And this is just coming off the top of my head, right? So we said that water has adhesion and cohesion, right? So because of those hydrogen bonds, it's going to decrease the temperature changes, right, in the body. So that's why we don't boil. It has different properties in different states. So we talked about ice being less dense than the liquid form of water, and why that's important to life, right? It's also the solvent of life. So it's a polar molecule that allows the other polar molecules to be dissolved. It's also a weak buffer, okay, in the body. So it helps to keep the pH of the body neutral. So what are some of these definitions? So cohesion versus adhesion. So think cohesion is the sticking together of the same type of molecule. And then adhesion is the sticking of a molecule to other substances. Okay, so water has both cohesion and adhesion, which then creates surface tension with the cohesion. Okay. And then thermal energy versus heat. Thermal energy is the amount of energy needed needed to be put into the molecules to create movement in the molecules. And then heat is the transferring of that thermal energy from a warmer substance to a cooler substance. And then evaporative cooling is how we cool ourselves down, right? So the molecules with the most energy can go to the surface and be released as sweat, okay? And then a solution is both a solvent and a solute. And a solvent is the thing that's doing the dissolving, and the solute is the thing being dissolved, such as water as the solvent and salt as the solute. And then an acid and a base, right? So a pH scale tells you how acidic or how basic a solution is. And then an acid is something that's going to donate hydrogens into the solution. And a base is something that's going to take up hydrogens from a solution, okay? Or you can kind of think as an acid being positive, base being negative. That's another way to kind of think about it. And then a buffer is something that can donate hydrogen when it needs to and take up hydrogen when it needs to keep the pH from changing, okay? All right, well, that was a long lecture, and I hope you guys are doing well, and I'll see you guys in office hours. Thanks a lot. Bye.